When DNS isn't working as expected, two command line tools give you authoritative answers, dig and nslookup. Both query DNS servers and return the results, but they have different strengths. Dig, Domain Information Grouper, is the modern, preferred tool for DNS diagnostics. It's available on Linux and macOS by default, and you can install it on Windows. It provides detailed output including TTL values, authoritative server information, and query timing. nslookup is older but universally available, including on Windows without any installation. For quick checks, it's perfectly adequate. Understanding these tools separates developers who wait and see from those who can precisely diagnose DNS issues. When a user says the site isn't working, you can query the DNS from their geographic region to determine whether it's a DNS issue, identify exactly what they're resolving to, check whether the issue is in the authoritative server or a resolver's cache, and verify that DNS changes have propagated. This chapter covers the complete toolkit, basic queries, advanced dig options, reading the output precisely, and common diagnostic workflows for real deployment scenarios. By the end, you'll be able to look at dig output and immediately understand what record exists, what TTL is remaining, which server answered, and whether the answer is authoritative or cached. Dig sends DNS queries and displays the results. The basic syntax: dig, options, name, type. The simplest query: dig mmap.com. This queries for a records using your system's configured resolver. Understanding the output sections, the question section shows what you asked for. Example: mmap.com. In a means, what is the record for mmap.com on the internet? The answer section shows the DNS response. Each line is a record, name, TTL, class, IN equals internet, type, name, etc., and the record value. If this section is empty, no record of that type exists. The authority section shows which nameservers are authoritative for this domain. If your answer came from a cache, non-authoritative, this section shows which nameservers have the authoritative answer. The additional section provides supplementary records, often records for the nameservers mentioned in authority. The statistics at the bottom: query time, 45 millisecond, how fast the response was, server, 1.1.1.1 hashtag 53, which resolver answered your query, when, timestamp. The flags line is important. Flags, QRRDRA. QR means query response, RD means recursion desired, you asked the resolver to do the work, RA means recursion available, the resolver is willing to. If you see AA in flags, it means authoritative answer, the response came directly from the authoritative nameserver, not a cache. A reference of the dig commands you'll use most often for DNS diagnostics. Query by record type: dig mmap.com A IPv4 address records. Dig mmap.com quad A IPv6 address records. Dig mmap.com name, canonical name records. Note, if the name resolves to a name and then to an A record, you see both in the answer section. Dig mmap.com MX, mail exchange records. Dig mmap.com TXT, text records. Important for checking Let's Encrypt verification and email authentication. Dig mmap.com NS, nameserver records. Shows which nameservers are authoritative. Dig mmap.com SOA, start of authority. Shows the serial number and timing parameters. Query against a specific resolver: dig at 8.8.8.8 mmap.com queries Google's public DNS. Dig at 1.1.1.1 mmap.com queries Cloudflare's public DNS. Dig at 208.67.222.222 mmap.com queries OpenDNS. Dig at ns1.cloudflare.com mmap.com queries Cloudflare's nameserver directly, bypasses all caching. Output formatting: dig plus short mmap.com, only the answer, no headers. Great for scripting: IP equals 42.187.212.75. 124.223.144.57. 43.140.62.242, dig plus null plus answer mmap.com, shows only the answer section. Dig plus trace mmap.com, traces the full resolution from root servers down. Dig x165.22.58.101, reverse DNS lookup. What hostname does this IP map to? Let's look at a real dig output and understand every field. When you run dig mmap.com, the answer section might look like mmap.com. 3247 INA 165.22.58.101. Breaking this down field by field: mmap.com. The fully qualified domain name, FQDN, being answered. The trailing dot represents the DNS route. 3247, the TTL remaining in seconds. This record will be cached for another 3247 seconds, about 54 minutes. This tells you it was originally cached with a higher TTL and has been cached for some time. IN, the DNS class. Always IN for Internet records. A, the record type. You asked for a records and got an A record. 165.22.58.101 the value. For an A record, this is an IPv4 address. If the answer section shows multiple lines, each is a separate record. For A records, multiple IPs mean round-robin load balancing. For name chains, you see the name followed by the final A record. If the status field, in the header, shows next domain, the domain doesn't exist. Nora with an empty answer means the domain exists but has no record of the requested type. Servfail means the DNS server couldn't process the query, often a misconfiguration at the authoritative level. Dig plus trace mmap.com shows the complete DNS resolution chain from root servers to your authoritative answer. This is invaluable for diagnosing delegation issues or a domain doesn't resolve correctly because the delegation chain is broken. What plus trace does, instead of asking your recursive resolver to look up the answer, Dig does the recursive resolution itself, step by step, and shows you each hop. The output from Dig plus trace has multiple sections. First, it queries a root server and gets back the list of .com TLD nameservers. You'll see lines like, 1728001ns.gtld-servers.net. Then it queries one of the .com TLD servers and asks about mmap.com. It gets back your domain's authoritative nameservers, mmap.com. 1728001nsns1.cloudflare.com. Finally, it queries your authoritative nameserver, ns1.cloudflare.com, and gets the actual A record. What to look for: if the chain breaks at the TLD level, your NS records at your registrar might not be pointing to the right nameservers. If the chain breaks at your authoritative nameserver, the record might not exist on your nameserver, or the nameserver might not be responding. If the chain completes successfully, the A record in the final answer is the authoritative answer, not cached. The flag AA, authoritative answer, will appear in the flags line. Dig plus trace is particularly useful when a record doesn't resolve but you're not sure whether the problem is the authoritative server or a caching issue. Trace bypasses all caches. nslookup is available on every operating system including Windows. It provides less detail than Dig but covers the common use cases. Basic usage: nslookup mmap.com. This shows the DNS server used and the result. The nslookup output, non-authoritative answer, tells you the response came from a cache, not directly from the authoritative nameserver. Name, mmap.com. Address, 165.22.58.101 inch is the result. If you see next domain or can't find mmap.com, the domain doesn't exist from the queried resolver's perspective. Querying a specific type: nslookup type equals mxmmap.com or nslookup query equals txtmmap.com. The type flag lets you query any DNS record type. Querying a specific server: nslookup mmap.com 8.8.8.8. This queries Google's DNS resolver instead of your default. Interactive mode: run nslookup without arguments to enter interactive mode. You can then type queries in change settings. Type server 8.8.8.8 to switch to a different DNS server. Type set type equals mx to change the query type for subsequent queries. Windows specific: on Windows, nslookup is built in. You can't easily install Dig on Windows without additional tools, like the Windows subsystem for Linux or bind utilities. For Windows, nslookup is sufficient for most DNS diagnostics. Quick comparison: Dig is better for Unix, Linux/macOS, more detailed output, better scripting support. nslookup works everywhere and is faster for simple queries. When mmap.com doesn't resolve, follow this diagnostic workflow using Dig. Step 1: check if the domain exists at all. Dig mmap.com. Is the answer section populated? If you get next domain, the domain doesn't exist from this resolver's perspective. If you get Nora with empty answer, the domain exists but has no A record. Step 2: check against your authoritative nameserver. First find your nameserver, dig mmap.com ns. Then query it directly, dig at ns1.cloudflare.com mmap.com a. If this returns the right IP but your local resolver returns nothing, you have a propagation issue. The authoritative answer exists but resolvers haven't picked it up. Step 3: check multiple resolvers. Dig at 8.8.8.8 mmap.com, dig at 1.1.1.1 mmap.com. If some resolvers return the correct answer and others don't, it's a propagation delay. The authoritative record exists but some resolver caches haven't expired yet. Step 4: check what your system's resolver is using. The server line in Dig output shows which resolver answered. If it's 192.168.1.1, your router's DNS is caching a stale record. Flush your local cache. Step 5: use plus trace to verify the delegation chain. Dig plus trace mmap.com. If the chain breaks at any point, you found where the delegation is misconfigured. Step 6: check TTL of existing records. If the answer section shows your old record with a high TTL, that tells you exactly when it will expire. Wait it out. When getting SSL certificates from Let's Encrypt using the DNS challenge method, you need to verify that the TXT record was correctly created and is visible to Let's Encrypt servers. The DNS challenge, Let's Encrypt tells you to create a TXT record at _acme-challenge.myap.com with a specific value. Let's Encrypt then queries this record from its own servers. If the value matches, it issues the certificate. Checking the TXT record, dig_acme-challenge.myap.com TXT. The answer section should show your TXT record. Example answer, _acme-challenge.myap.com. 300 INTXT ABC 123 random value. If the record doesn't appear, the record might not have been created correctly, or you might have created it with the wrong name. The name must be _acme-challenge followed by your domain, not just your domain. Checking from Let's Encrypt's perspective, Let's Encrypt uses their own resolvers. To check what they'll see, query against multiple well-known public resolvers, dig at 8.8.8.8 _acme-challenge.myap.com txt and dig at 1.1.1.1 _acme-challenge.myap.com txt. If these return your TXT record, Let's Encrypt will almost certainly see it too. Timing, Let's Encrypt's validation happens when you run certbot. If your TXT record has a low TTL, like 300, it should be visible globally within a few minutes of creation. Add the record, wait 5 minutes, then run certbot. Certbot DNS Cloudflare. If you use Cloudflare and the certbot DNS Cloudflare plugin, the DNS challenge is handled automatically. The plugin creates the TXT record, waits for propagation, runs the validation, then removes the record. Forward DNS maps hostnames to IPs. Reverse DNS maps IPs to hostnames. Both are useful for diagnostics. The reverse DNS lookup command, dig_x_IP_address or nslookup_IP_address. Example, dig_x165.22.58.101. The answer section shows 101.58.22.165.in-address.arpa. 3600 INPTR_myap.com. The PTR record maps an IP back to a hostname. When reverse DNS matters, email deliverability, mail servers check whether the IP sending email has a PTR record matching the domain. Without a PTR record, or with a mismatch, your email may be marked as spam. Your server's IP should have a PTR record pointing to your mail server hostname. Security tools and logs. When analyzing access logs, tools can look up the hostname for each IP. If your server has a PTR record, your server name appears in logs instead of a raw IP. Diagnosing who owns an IP. If you're getting attacked from an IP, dig_x_attacker_IP can reveal the hostname, sometimes indicating the attacker's hosting provider. Who sets PTR records? Not you, in most cases. PTR records are set by whoever owns the IP block, usually your cloud provider. In AWS, you can request PTR records through the support console. In DigitalOcean, PTR records are set automatically to your droplet's name. In Oracle Cloud, you can set PTR records in your VCN settings. Checking your server's reverse DNS, dig_x_server_IP. If you get a result like server-165-22-58-101.example.com, that's the default PTR your provider set. To change it, contact your provider or use their control panel. A practical scenario testing understanding of dig output. You run dig at 8.8.8.8 myap.com and get this output in the answer section, myap.com. 12 INA 1.2.3.4 Your colleague runs the same command from their machine an hour later and gets myap.com. 3599 INA 5.6.7.8 Both commands query Google's DNS at 8.8.8.8. What's happening and which IP is correct? Option A, there's a DNS inconsistency bug, both IPs shouldn't exist at the same time. This isn't a bug. It's an expected behavior. Option B, your colleague's query went to a different Google server that has the old record. Google's 8.8.8.8 is anycasted, queries may reach different servers. But both serve the same data for a given domain, so this doesn't explain different IPs. Option C, you queried at a time when Google's cache was about to expire, TTL 12 is equal to 12 seconds left. Google requeried the authoritative server and got the new record. Your colleague queried 5 minutes later and got the new record with full TTL of 3,599. This is the correct explanation. TTL of 12 in your query means the cached record was about to expire. Google requeried and your colleague got the fresh answer. Option D, you queried while a DNS failover was in progress. Possible but wouldn't explain the TTL values precisely. The answer is C. The TTL in dig output tells you how stale the cached record is. TTL 12 means the record was about to expire. TTL 3599 means it was freshly queried and cached with a 3600 second TTL. This is normal DNS cache behavior, not a bug.